Okay, so on the top, we're going to have the 35 to 44, and on the bottom, we're going to have the 45 to 54. Okay, going over to the table itself, this is 136. And over underneath that is going to be the 172. Okay. Now, of course, we have to ask if we reduce it, and both of those are even numbers, so yes, we can reduce it. Let's just start with 2's. We could actually go to the prime factors and get it very quickly. Why not? The prime factors are so quick, let's just do that. Okay, so 2 times what? This is going to be 63, is that right? No.
A little more than that.
A little more than that.
78.
Yeah, that's right. Okay, that's still a 2. That's going to be 35, and 4 is 39. 39 actually is not prime. That's 3 times 13. And that's it. Okay, 172. Okay, again, let's do that. That's going to be 2 and 6. No. 8 and 6. Okay, and this is a 2 and 43. Now, is 43 prime? That's
Well, you're going to have to go back on that one. It's 78, 68. Yeah, 68. My bad.
Over here?
Yeah.
Yeah, 68.
6 and 1, yeah, that's right, 68. Okay, that changes this. That's going to be 34. Oh, it's a shame we get rid of the 13 now. Okay. And that gives you 17. Well, 17 is prime, that's for sure. Okay, are we done over here? Let's see. Yeah, because that's 43 is prime also. All right, so what we have here is the product of these primes, which is a 2 times a 2 times a 2 times a 17 on top, and these primes, 2 times 2 times 43 on the bottom. Okay, now we cancel the common factors, and we get 34 on the top and a 43 on the bottom. And there's nothing common inside those, because these two are primes. So that's it, 34 over 43. That would be called the ratio of 34 to 43. Is that okay? Okay. Question?
I don't know how I got it, but I think I got 136 and I left it the same as 183 because everything went into the top and the bottom and stuff. Right. And like the 136 just stays the same like that.
So you found a large factor that goes into all of them.
43 and that's it.
Yeah. Well, the largest factor that goes into both of these is 4. So you can see that right here. The two twos came, which is 4. So that's as much as it's common to both top and bottom. Everything else is not common. So the only thing you can divide into top and bottom is 4, the largest thing. Okay, still in 5.1, anything else?
Number 37?
37. Okay, the temperature at 8 a.m. in Los Angeles was 66 degrees. By 2 p.m. it had risen to 90. All right. We're at a ratio representing the increase in temperature to the temperature at 8 a.m. All right, remember the first thing they tell you is in the numerator, the second thing they tell you is in the denominator. Okay, so here we are. In the denominator, we want the temperature at 8 a.m. Well, that's 66 degrees. All right, the increase in temperature would be to subtract these two upside down, of course. 24-degree increase, huh? So that's what goes up here. And then, of course, it's a matter of reducing 12 to 33 and so forth. And no, there's more in there, isn't there? Yeah, there's a 4 over 11, yeah. So it's the ratio of 4 to 11. Yeah. That's the increase in temperature to the temperature at 8 a.m. The important thing is getting that increase. That's the fraction. Okay? Any others?
29?
29. 16 4/5 to 8 9/10. 18 9/10. Okay, they want the ratio of lowest terms of whole numbers in the numerator and denominator. And again, this tells you how to form the ratio. But since we're going to form a fraction, which is really a division problem, and we're doing it with mixed numbers, we better change the mixed numbers into impropers, because you can't divide the mixed numbers. Or at least it's very difficult. All right, 5 times 16 is going to be 80, and 4 is 84/5. And we want the ratio of that to 189/10. Okay, it's going to look like this. Question? It's going to look like this. In the form of a fraction, it's going to look like 84/5 divided by 189/10. But that's called a complex fraction. There are such things in mathematics. They're pain. You know, people think, what is it? What do I do with it? So it's much easier to write this the following way. Just write it out with a division sign. And then flip it over and multiply. So this would be 84/5 times, flip that over, 10 189ths. Okay. Well, we can do some canceling here. And that's about it, I expect, huh?
168.
9 and 8 is 17, 18. Oh, okay. Yeah, 3 does go into both of those, huh? Yeah. Okay, 3 goes into that 63 times. 3 goes into that 28 times. Yeah. And then 2 times 28 gives you a 56 over 63. Question is, can that be reduced? Yeah, it has to be. Yeah, that's in 7 times 9 is 63, and 7 times 8 is 56. So this is 8 over 9. That's right. Because 7 goes into both of these. Yeah, 8 to 9 is the ratio. Yeah. Certainly not obvious when you look at it like that. If that's the ratio of 8 to 9, no, that's not obvious at all. Got to play with it. Okay. Any others in 5.1? Let's go on to 5.2 then, the rates, which are very similar. It's just that rates can have different units. And
can you tell me on the on number 29, how did you find 8/4, and then how did you make it into?
This one over here? Okay.
Yeah, 84.
5 times 16,
Yeah,
that's,
I'm struggling with that.
okay. 5 times 16 is 80, and then add the 4 gives you an 84/5. So we're converting it to an improper. So you multiply denominator times whole number, and then add the numerator, so you get 84/5. Okay. All right, let's go on to 5.
I understand, but
anything there?
how do you reduce it to become? How do you reduce 84 to become 8? The answer that you got. How did you reduce the 84 to?
Over here?
Yeah, yeah, right there.
All right.
How do you reduce it? How?
It has to do with the fact that these two numbers, 63 and 84, if you add the digits, they add up to a number that can be divided by 3. 6 plus 3 is 9. That can be divided by 3. And 8 plus 4 is 12, which can be divided by 3. So it's the divisibility rules. That means 3 into 63.
Oh, okay, I got it. Okay.
Okay, you got it from there on. Okay, good. All right, we're in 5.2. Any questions? Very similar ideas, but you can have different units in rates. 13.
You doing number 13?
I'm doing number 13.
Thanks.
Okay. says write each rate in lowest terms. Tyler earned $58 in 8 hours. Okay, now the fact that we have dollars here and hours there, that's perfectly okay because we're talking about a rate. They want us to write the rate, but in lowest terms. Well, the rate would be written as a fraction. It's the rate of 58 to 8. And yes, you can put dollars here. In fact, you really should put them there. Okay, but the point is, they ask for lowest terms here. Now, lowest terms is not the same thing as a unit rate. Okay, for a unit rate, you'd have to divide top and bottom by 8 to get a 1 down there. That would be the unit rate. But they're not asking for that. They're asking for lowest terms, which means take out all possible common factors for this and this. All right, they're both even, so it's worthwhile trying 2. 2 goes into that 4 times, and 2 goes into that 25, and 4 is 29 times. So you get 29 over 4, and 29 is a prime. 4 is not, but 29 is prime. So that's it. This is the lowest terms. It would be $25 for 4 hours. That's not the same as the unit rate. Okay? They're asking for different things. It just asks you to reduce a fraction. That's all it is. Any others in 5.2?
21B, I'm not sure why that does not, it's not a unit rate.
21, okay.
Yeah.
21D, did you say?
B.
B as in boy?
B is in boy.
Okay. Okay, on the following rates, identify those that are unit rates. And this is written as 333.2 miles over 14 gallons. Okay, the reason why it's not a unit rate is because that 14 is not a 1. Now, if you wanted to make it into a unit rate, you'd look at that denominator and say, what do I divide 14 by to get 1? And obviously it's 14. So you divide that by 14, but whatever you do down here, you have to do up here. So 14 would have to be divided into 333.2, give you a completely different, the fraction would be the same, the rate would be the same, but it would have a denominator of 1. Then you'd have a different decimal on it.
Is it just because of 14? You said you could have a 1
That's
down
right.
there.
Basically, the answer to your question is this is not 1.
Ah.
For a unit rate, it has to be 1. Yeah.
Oh.
Okay? Any others? 29. At the market, bananas cost $1.50 for 4 pounds. They say determine the unit rates and round to the nearest hundredth when necessary. Okay, $1.50, 4 pounds. All right, for a unit rate again, just do what you have to get that to be a 1. Well, obviously divide by 4. But then you have to divide the top by 4. So basically, you're always dividing the denominator into the numerator. It's a decimal division in this case because we're working with money. The monetary system is decimal. So 4 into 15, 3 times 4 is 12, and so forth. 7 times 4 is 28. And the question is, how far do we go with this? This is a 2. Well, this one is actually going to terminate, because 4 into 20 is 5. So the answer to this is 0.375, and that would be dollars. We would write it as dollars per pound. In other words, 37 cents, and then you have a half of a cent there. And we don't have a coin for that. That's not in our monetary system, but they say to take it out to the, they want to round it to the hundredths. Okay, to round that to the hundredths, that makes that into an 8, so it would be 0.38 per pound. But in order to get that rounding to the hundredths, you got to go out to the thousandths position on your decimal division. Any others? Yes.
47.
47. Carbonated beverages come in different sizes and contain different amounts of sugar. Compute the amount of sugar per fluid ounce for each soda, then determine which has the greatest amount of sugar per fluid ounce. When my daughter was very young, they had a science fair in Pacific Grove, and we went over there. She entered something, I don't remember what it was now, but we went over to this little experiment. This is always done at every science fair in the world, right? They have different sodas, and they put something that resembles tooth enamel into them and leave them there for a couple days, and then bring it to the science fair. And that really impresses the kids, I'll tell you. And this is very similar to it. All right, we got Coca-Cola. And most people say, oh, that's got to be the worst. Well, you're right. Mellow Yellow, which I have never seen. I think it's an East Coast thing. And then there's ginger ale. Okay, this is the way the table presently stands. It says the amount. That's the amount of ounces in the can. This is 20, this is 12, and this is 8. And then the amount of sugar that's listed on the side of the can. 65 grams, oh wow, 47 grams, and 24 grams. So we can extend the table a little bit, just add another column to it, and we can simply calculate what they ask us to do. Compute the amount of sugar per fluid ounce. So this would be sugar per fluid ounce. This is in fluid ounces. By the way, just so we can get some training on units, the system, what we call our American system, is confusing. When you're ready. Okay. The American system is confusing. Ounces have to do with what? Anyone know what that does? What does that measure? Yeah, it's a measurement of weight. That's what ounces are. Yeah. Fluid ounces? No. They're not a measurement of weight.
Is it like?
They're a measurement of volume. Volume, yeah. Or capacity. Okay? And it gets even worse. I mean, our system is a cut and paste thing that's gone on over hundreds of years. And, you know, people who come from other countries where the metric system exists come here and spend their life in confusion. They say, why are you doing things that are so confusing? You know? We'll get to a chapter on that, and you'll really appreciate the metric system, and you'll want us to switch right away. Well, they've been trying to make us switch to the metric system for at least a century. There's a little bit of resistance in you know where. Congress. Right. All right, so we want sugar per fluid ounce, which means we're going to have to take that 65 and divide it by 20 there, and the 47 will have to get divided by 12 there, and the 24 will have to get divided by 8 there. When you do all that, these are the following results that you get. Coca-Cola is 3.25 grams of sugar per fluid ounce. Now, a fluid ounce is a rather small amount of volume, okay? That's pretty small.
Yeah.
And there's 3¼ grams of sugar in that tiny bit, okay? I mean, that's almost the total amount you're supposed to have in one day, you know? Not one can. All right, this turns out to be mellow yellow is 3.92 grams per fluid ounce. And the ginger ale turns out to be 3 grams per fluid ounce. So, which is the worst? Well, strangely enough, mellow yellow comes out worse than Coca-Cola. Now, as I say, I've never seen any of that. Has anyone ever seen mellow yellow? You got it? Where is it?
No.
I'm from the East Coast.
Where?
East Coast. East Coast?
East Coast.
Yeah.
Okay. Anyone else? Yeah, you've seen it, huh? Okay, so basically, don't buy it. Really? That's huge. That's almost 4 grams in a fluid element. Anything else in 5.2? You can see this is the use of rates and so forth. Okay, so let's go on to an extension of this idea, which is called proportion. Now, everyone's heard the term rates. Some people have heard the term ratios. And everyone's heard proportions. You know, we say, oh, yes, well, that's very proportional, as if we understood what it meant. But we're going to understand the mathematics of it now. Proportions are a statement that two rates or ratios are equal. Okay? So, this is actually something we've dealt with before, but we didn't call it this. If you take a fraction like 1/3, and you multiply top and bottom by the same number, you recall we don't get a different fraction, we actually get an equivalent fraction. In other words, if you punched the new fraction in, you would get the same decimal readout on your calculator as you get for 1/3. I'm going to multiply top and bottom by 2 to get a 2 there and a 6 there. This is a statement that these two fractions are equal to each other. Now, they could represent rates or ratios, you know, but the point is, they're equal. They're equivalent fractions. So we've seen this before. And back when we did see this, we found that there was a way to check to make sure that two fractions really are equal, a very quick way, and it's simply called cross multiplication. So you take the numerator up there, multiply by that denominator, it should be equal to this numerator times that denominator. Of course it is. 1 times 6 is equal to 2 times 3. Yes, that is a correct proportion. Okay? Okay, well what's going to happen now is we're going to develop the ability to check proportions even when they're kind of strange numbers, like decimals and even mixed numbers in the proportions. Don't do your intuition thing on these things because it'll never work, I guarantee you. You got to check it with that process, cross multiplication. And we'll also see a different notation for this. In fact, let's look at the new notation. We found out that an older kind of notation for 1/3 is 1:3. And that's pronounced in English 1 to 3. Okay? Could be a ratio of 1 to 3, comparison of 1 foot of board to 3 feet of board, and so forth. Okay, that's the older notation. Now, is there a notation for a proportion that keeps the colon notation? Yes, there is. Looks like this. You take that particular fraction, 1 to 3, write it down with the colon in between. The equal sign becomes a double colon like that, and then you write down this fraction, 2:6. Chances are this is the way your parents or maybe even grandparents learned this topic. And this cross multiplication is memorized or was memorized by them using this structure in the following way. These two numbers are called the means. And means, one of the older definitions of the word mean is middle. Those are in the middle of this proportion, inside, so to speak. Whereas these two numbers are called the extremes. So they learn the following sentence. The product of the means must equal the product of the extremes. So that was their way of doing it. Yep, that's what you find in the older books. And sure enough, that's right. 3 times 2, 1 times 6. Yep, product of the means equals the product of the extremes. That's how you check a proportion. So let's check to see if some of these are true. We'll do some simple ones and then we'll go on from there. Suppose we take the ratio of 3 to 5 and see if it's really equal to the ratio of 9 to 15. All right, cross multiply. That's the only test we have. The product of the means equals the product of the extremes. So is 3 times 15 equal to 5 times 9? Well, that's 45 and that's 45. And the answer is yes. So this is a correct proportion. Okay, it's that simple. Some of them are not so easy to figure out. 1 2/3 is proportional to 4. Question is that equal to 10 proportional to 5 1/2? Okay, now there goes all our intuition about proportions and ratios, right? So when it makes a number, that's it. Our intuition goes down the drain. Well, that means we're still going to have to go back to the cross multiply thing. Question is 1 2/3 times 5 1/2 equal to 4 times 10? Well, that requires some calculating, huh? So we switch over into impropers. 3 times 1 is 3, plus 2 is 5/3. 2 times 5 is 10, plus 1 is 11/2. Okay, we cancel if we could, but we can't. So that's 55 on the top, 6 on the bottom. Is that equal to 40? 4 times 10. Well, 6 goes into 55 how many times? Well, 6 times 9 is, yeah. And so this is just a tad bit over 9. Huh? If you divide 6 into 55, it's just a little bit over 9. Is that equal to 40?
Yeah, I'm close.
No. So the answer is no. These are not proportional. Not. Okay? But you never guess that by looking at them because of all the mixed numbers. You actually have to do the calculation. Same thing with decimals. Not so easy to see. We'll look at this one. 2.7 is to 5.3 as 8.1 is to 15.9. And the question is that true? Again, cross multiply. So is 2.7 times 15.9 equal to 8.1 times 5.3? And for that, you know what happens. We depend on Canon and Texas Instruments and so forth. All right, let's see. 2.7 times 15.9. This says 42.93. So is that equal to 8.1 times 5.3? Strangely enough, the answer is yes, it is. So this is a correct proportion. But again, with decimals, not obvious. Okay, now what we're going to do is take this into, are you ready for this? Algebra. Oh no, I'm not ready.
Finally. I've been waiting for it.
Oh yeah, okay.
Wanting to learn it.
In general, a proportion looks like this. A is to B as C is to D, where A, B, C, and D can be 4 numbers. You check, cross multiply, and so forth. That's just what we do. Right, but what if we have only 3 numbers and one of those remains a letter? Okay, see, the only difference between arithmetic, as we've learned it, we've gone through a lot of arithmetic so far, and algebra, is that algebra throws a few letters in. It's just fancy arithmetic with some letters thrown in. That's it. Really, that's nothing more to algebra than that. So let's say, let's take it one out of the book so you can see it in the book. Suppose we looked at something like this. We got x over 20, and x is the prime choice for an unknown in algebra. So we'll just use it. X is to 20 is 3 is to 4. All right, now, yes, cross multiply, but even when you cross multiply, you're going to have to do something with that unknown, that x. Now, please listen, because this gives you the key to algebra. We don't know what x is, but we do know it's a number. Okay? So we treat it like a number. All right? Which means we keep on doing our process just like we did with two numbers. We're going to multiply an x times a 4 here. All right, let's do it. X times 4, I'm going to write it as 4x. Over here, 20 times 3. Now, watch this very carefully, because you haven't seen anything like this probably in quite a while. Okay? Yes? How could you have a question yet?
No. I have the answer.
Oh, no, I don't want the answer. All right, the process is much more important than the answer. Seriously.
Okay.
Yeah, the process is crucial, right? All right, what we have here is 4 times x is equal to this. Well, let's just write out what that is. That's 60, okay? All right, now the numbers are so simple here that we can actually use English to figure this out, right? If you called x what number, you don't know what it is, so call it what number. Put it in English, okay? What number do I multiply by 4 to get 60? There it is. Pops right in. What is it?
15.
Yeah. Obviously, x is equal to 15. Okay? Now, you can be sure if I threw a few decimals in here or mixed numbers, that would not happen. The pop-in wouldn't happen, right? Okay? You'd be sitting there with a Zen mind. Okay. So we have to develop a technique to do this. Something that doesn't depend on our minds sort of intuitively getting the result. Okay? So here's the technique. Think of this equation as a set of balance scales. In a sense, what the equation is saying is the left side is exactly balanced by the right side. Please put away phones. This is going to get you through algebra, believe it or not. All right. If these things are in balance, and you still want to find out what that x is, but it's multiplied by 4, you take those two ideas into your mind and you say, what can I do to get x by itself? Well, I got to get rid of the 4. How do you get rid of the 4? It's multiplying the x, so therefore I can undo the multiplication by 4 with a division by 4. Okay, that's certainly a plan. If I divide this by 4, yes, 4 and 4 cancel because they're multiplying their factors, so you can cancel the 4s. Okay, there's my x, good. However, I got to remember I'm working with something that's in balance. Okay? So if I do something to one side, think of balance scales. I know they haven't been around for many years, but they used to have them in the chemistry department. They'd actually have analytical balances there. Okay. Think of a pair of scales. You did something to one side, you better do the same thing to the other side or it's going to go out of balance, wouldn't you say? Okay, so I'm going to take the very same 4 and divide it into the 60. Now it's a division problem, no longer intuition. A division problem. 4 into 60, 15. Okay, and we're going to follow that all the way through this process of proportions, because we're going to put unknowns in all 4 positions. I put one up in the upper numerator up here. You can put one down here. It doesn't matter where it is. Still, you're going to end up having to do a division on both sides of the same number. Okay? That's one of the fundamental techniques of solving equations. Now, there's many more. We might get to a little bit of it in our class later on.
Isn't this the least common multiple, basically, we're talking about here? Using it up here?
Yeah, that idea is more like the English sentence. What do I multiply 4 by to get 15?
Right.
Yeah, look for the multiple of 4 that gives me 60.
Right.
Yeah, that's true. But you start throwing in decimals and mixed numbers, and there it goes, right?
Yeah.
That doesn't
Yeah.
work.
Yeah, it's true.
So you have to have a procedure. Okay. Yes,
So all you did was just replace the X with the 4 then, basically?
say again?
So all you did was just replace the X with the 4? So you just,
No, what I did was, I said, I've got to undo this multiplication by 4. That's 4 times x, okay? So I've got to undo a multiplication process. The way you undo multiplication is with a division by the same number. See, because 4 into 4 is 1.
yeah.
Ah, I've got a 1x there. Well, you don't write the 1, so there it is, there's x. So in this case, I'm undoing multiplication. Now, we'll get to a much bigger scene than that. We'll look at addition, subtraction, multiplication, division, but that's later on. All right, let's do another one. Suppose we had this. We have x is to 13 as 6 is to 39. And what we're saying is, tell me the value of x which makes that true. It makes the proportion true, okay? Well, if it's true,